See, this is the core architecture of USB 2.0. Okay, in these, how many interfaces you people can see here? This is called protocol layer, UTMI or ULMI interface, that is between protocol layer and file layer. Basically, file will deal with directly analog world, and protocol layer deal with digital world. It will convert from analog to digital and digital to analog and analog. These things it will do. It have 40 pin. For 12 pin we will use ULMI for reduced pin count. Okay, here major role will be played by the CSRs, control and status registers. So by configuring, whenever that enumeration happen, through the enumeration we will configure these registers. Based on its configuration, it will act accordingly. Whatever way we are configuring CSR registers, so our device will act accordingly. Whenever we will call it is as SOC level. Whenever power on reset POR, then all the states will be initialized to its initial values. After that, after in next minute, in next passage of the clock, those will be first thing is enumeration process. Enumeration process means the host needs to understand who the device is, whether the device is a mouse or a keyboard or a flash drive or any other USB connected. See, USB has a various things actually. Okay, USB C also will be there, that we can connect through the mobile. What is the device it is connected to? That information will be present in the USB device configuration space. So we will read that configuration space. Space will be fetched by the host via read operation. It will understand first who the device is. After that, that is called enumeration process. Okay, after enumeration process we will have speed negotiation. Okay, whatever may be that endpoint device having, always host is having highest speed only. Okay, in a protocol layer 480 mbps is the highest speed. So ours is either uh, full speed or high speed. We have three speeds. Low speed from USB 1.1 legacy one, that is. After that 1.5 mbps, that is. After that full speed, that is 12 mbps. Most of the devices have that 12 mbps. 480 mbps we'll call it as a high speed, that is present in only a few components. Most of the hosts consists of that in some cases the other way around will also be happen actually. Okay, so here we have external SRAM memory, memory interface and arbiter, because this wishbone is a simple open source bus. These people has considered function to microcontroller. This is functional interface. So the function we will give it to the microcontroller. Microcontroller have a firmware or software. That software is used to configure these registers. Okay, through SIG, serial interface engine, SIE, serial interface engine. So that serial interface engine will have that what we call a state mission. Through state by state it will do configuring all those things. Okay, after that here one thing is missing. That thing is DMA is also present. For example, if you want a chunk of the data transfer from directly into the memory, Okay, then we better that core will offload its job to the DMA, so that DMA will transfer from one place to the another place. That's what DMA will do actually. Here we have two clocks. The clocks controlled by microcontroller, and the clocks deal by the protocol
Tissue paper.
the the protocol here, unlike this is a serial bus, right? UTMA, UTMA will get a bus, okay? Whether it is 8 bit or 16 bit, based on our clock frequency will differs. We usually think like 480 Mbps high speed it is working means our clock frequency should be 480 megahertz. That is the basic conception, misconception. So it will override that. It will make it is like a, if it is a 8 bit one, then 480 divided by 8, 60 megahertz. If it is 16 bit, 30 megahertz clock only sufficient. This is at the parallel level. What is the bus width? Based on that, our clock will choose. Okay. By default, 8 bit has taken, so 60 megahertz clock these people has taken care. Say host interface. To talk with the host, it needs an interface that will be wishbone. Okay. Bandwidth. Theoretical throughput is, what is the difference between bandwidth and throughput? I would like to give you a simple distinction. Bandwidth is theoretically calculated. Throughput also we will calculate theoretically, but in real time, how much it is with how much speed it is going, if we calculate, then that is called throughput. Okay. Bandwidth is basically what is the difference between maximum frequency to the minimum frequency, the difference of a channel. Okay, the bus width. But throughput is, da- this is data rate or baud rate. Data rates means per second how many bits it is transferring, and baud rate means per second how many symbols it is transferring. If we create more than one bit per a symbol, then we'll use the word baud rate. Memory interface and arbiter. See, here we have a, with the help of mux, if we wanna talk to SRAM, then through SRAM interface we are getting from this wishbone as well as protocol layer. These can be arbiter. Okay, this will take care of the orbiting, which one should go first. Okay. See, SRAM is a single ported SRAM block that is used for buffer the input and output data. Some small amount of data we will use it for the buffering purpose before it is even going to the actual memory. USB means whenever read and write transactions will be there, right? At that time we will store in some temporary buffers. That's what SRAM is. Now for example, if you take flash drive, only flash drive have some memory, right? That memory is not this SRAM. And if you take USB mouse or USB keyboard, those things doesn't even require the uh, uh, that memory space, right? But still it requires for writing and reading uh, that address space, configuration space, address space, as well as if if we press a key or press a mouse key, it coordinate need to transfer to the firmware. So those all the things will be taken care in the ssram. Okay. Single ported synchronous ram it is. What actually protocol layer will do, it will simply packet assembly and packet deassembly. Packet assembly will be done at the sender side, and packet deassembly will do it at the receiver side of both mac. In attached to the mac only we will do it. Okay. This is protocol engine, it will take care of this. See here, memory interface, whenever, and DMA is also included only because whenever we wanna transfer chunk of data from one place to another place. For example, from memory to the laptop, if you wanna transfer 4 GB 4 GB movie, at that time USB protocol will offload its work or job to the DMA, so that DMA will have a descriptors. What is meant by descriptor? It is also like a memory address. It's a data structure. So in that data structure, address will be there. After that, maximum packet size. Some fields will be there in a structure. Okay. So that structure, if we give, so it will go from the one place to another place with that maximum speed. That the source address, destination address uh, will be present. So from the source address to the destination address, it will store, it will continuously transfer. Obviously CSR registers will also be present. Okay. Yeah, what protocol engine will take in? Protocol engine's main job is to acknowledge the data transfer. Okay. They here, unlike ACNAC, here we have four types of responses will be present. What first one is ACK, second one is NAC, third one is NYET. Okay, not it. Other one is stall also. Okay, here we are using one special token. Here we will call it as a tokens. Okay, what is meant by token? It's a piece of information. It will tell like what kind of packet it is. Okay, here we will have some special kind of packets also, like ping is one of the special kind of packet. And ordinary transfers, memory read or memory write, or data transfer, data transaction, that is smoke kind of. Sanity or smoke. Sanity means only checking the clock and reset, and sanity means data transfer basically. This is some special kind of corner case we can say. Ping and SOF also, startup frame. This is also some special kind of token. It is startup frame, end of frame. Packet assembly. See, the block assembles the packet and places them into the output before. See, this is its job. First, what are the packet consists of means? Okay, the first assemble header inserting into proper PID. PID means packet identifier. And checksum means CRC. That CRC for a control word 5-bit CRC, for a data word 16-bit CRC will be there. If it is a control, then there won't be any data. That we call it as ZLP, zero length packets. Okay, only control packet that is. Then we will add data packet. Then we will add data field if requested. Data is requested means packet deassembly. We will extract, we will decode the PID and sequence numbers, and we will do obviously for data integrity checksum. UTMI. This interface block UTMI, component of file transceiver. Okay, universal transmitter receiver. Uh, this is interface this is. Okay, TXV4, RxV4, uh, interface state engine, speed negotiation engine. So this will take care. RxV4, Rx bus interface. Interface state engine. What it will do simply. This block tracks the interface state, in which state it is present. Okay, it controls the suspend and resume modes. What is meant by suspend and resume? See, whenever our device is ideal for a quite longer duration, it have its time units. That simulation time units will be present. If it is exceeds our simulation time thresholds given by the spec document, then it will go into the suspend mode other than active mode. So in suspend mode, it will draw very less power to save the power also, as well as unnecessarily if it is active. It will draw dynamic peak power, so device will get heats up unnecessarily. So to avoid that, it will go into suspend. Whenever we required, we requested or anticipated some action, then it will raise a request. It will raise a request. Through it will get an interrupt through that from the suspended mode to the resume mode. So active working mode it will come. Full speed means I told you for 12 Mbps, and high speed means 480 Mbps. If it want to switch also, directly it won't get switch. It will first suspend the operation. So after that it will switch again. It will come into the active. Internal state machine will track up the state and switching the operating modes. So these are the operating modes: full speed or high speed. Mostly low speed we don't use, but it still is there from the legacy. If any legacy device is connected, then it will work with the low speed. Speed negotiation block. Okay, what it will do? It will negotiate the speed of USB interface and handle the suspend and reset detection, and it will settle down to the lowest speed. For example, our host is at a high speed 480 Mbps, your device is at full speed, that is 12 Mbps. Then both speeds will negotiate and settle down to the 12 Mbps only. RX and TX FIFOs. The FIFOs will temporarily receive transmit data. Okay. RX and TX bus interface. These blocks ensure proper handshaking. Whenever either control or data is transferred from sender to the receiver, then that receiver should initiate its handshake through response signals like ACK, NAC, NYET, stall. These all things should ensure that RxTX bus interface will ensure that. See operation. See USB function. This is my core logic. This is connected to 5. Here USB cable comes. For example, you take an example of USB mouse. Okay. Here host or hub will be present. Hub is for connecting one to many. That's all. Hub here, instead of switch, why we are calling hub? Because it is also intelligent one. Okay, hub. It doesn't only routes. It will do some intelligent stuff. Okay. Here USB function. See, these functions will be connected to the E0 to N. So endpoints. These we will call it as endpoints. Endpoint to 2 cross 16. So 32 endpoints will be present actually in core logic. Okay. See, in the operation, the USB function controller first discusses the logical interface. These are the core. Okay. See, no software intervention is needed between different endpoint accesses. Double buffers may be set up. For each function, we will have double buffers means 2 buffers. Okay. 2 cross 16. That's why. reducing the latency requirements on the software and increasing USB throughput. Obviously, it will. Endpoints. See, this USB core supports up to 16 endpoints, 2 cross 16, strictly speaking, 2 endpoints for each function. The actual number of endpoints is set before the synthesizing the code. Okay. In this, the function controller must set to end up by writing the endpoint registers EPN, endpoint nth number CSR. In each CSR, we need to configure before even accessing endpoints. EPN interrupt, interrupt, endpoint interrupt, endpoint buffer X, buff 0, buff 1. Okay, the buffers. The buffers point to the input output data structure memory. Okay, value of all ones. 7 means triple one, right? 12 ones, so 15 ones. That much indicates the buffer not been allocated. Whether the buffers were allocated or unallocated will be present here. Okay, if all buffers are not allocated, the core will respond with a NAC, no acknowledgement. Okay, to the USB host. This USB core supports the double buffering feature. So two buffers, buff 0, buff 1 will be taken care by this, which reduces the latency because one buffer is used for the writing, another buffer for the reading. So you will get a simultaneousness here. Double buffering is enabled when all buffer pointers have been set. The data being retrieved or filled from to the buffers is in a round robin fashion. This is what kind of arbitration we are using. When data is sent to or from endpoint, first buff 0 is used. When the first buffer is empty or full, the function control may be notified by an interrupt. Okay, whenever it is coming to the full or empty, whether we are writing, it will become full. So interrupt will notify stating that you are it is full. So you switch to buff 1, buff 0 to buff 1. Okay, or else we are reading, fetching. So at that time it will notify, interrupt will notify that this is got empty. So you need to switch to buff 1, like that. When first buffer is empty or full, the function control may be notified via interrupt. The function control can refill or empty buffer 0. Okay, buffer to use buffer 0 again. So any buffer is not allocated will be skipped. A buffer has user bit set. So how we know that whether the buffer is being used or unused, allocated or not? We'll have one state called buffer state. In that buffer states, if it is a 0 means that is free. If it is 1 means it is allocated. The buffer that we will use with the buffer bits. Okay, the buffer used bits to indicate when buffer has been used in this information. Okay, a buffer may be larger than maximum payload size. See, most of the times this will happen, maximum payload size. Okay, we will have one threshold, but buffer size should be greater than that. Otherwise, if you wanna one maximum payload comes, after that if you can't fit it in one buffer, it will become a hectic job. To avoid that, our buffer size always greater than maximum payload size. We will call it as MPS. Okay, in that case, multiple packets will be sourced or placed from the buffer. So a buffer out for an out endpoint, that see that port directions, whether it is in or out, depends upon the buffers as well as that instruction itself. Whatever the that packet type is there in that token, PID token only, we will embed that whether it is in or out. So the buffer considered full and USB core will be switched to the next buffer. Buff 1, that is buff 0, this is called buff 1. Two buffers will be there. For example, if maximum payload size is 512 bytes and the buffer may be 512 1024 1536 2048 bytes larger. The software should always check the buffer size field. It should be 0 when the entire buffer has been used. That is called credits, right? Like credits only here also, that empty space will be checked before even doing an operation. The firmware's job is to check its empty space. The size field indicates how many bytes of the transfer have been used. Okay, if there is no such limitation for in buffers. See out buffers and in buffers. In buffers will intake the data, out buffers will outsource the data. The core will always transmit maximum possible number of bytes. The maximum number of possible bytes is always smaller than one of maximum payload size and remaining buffer size. See here, buffer operation. Initial buffer pointer will be here. First transaction, maximum payload size will be this. This transaction should be less than or equal to maximum payload size. Second transaction, maximum payload size. So buffer pointer after first transaction will come here. After second transaction will come here. So this is at the transaction. So actually the these buffers may or may not be continuous. See this buffer and this buffer, there might be a gap, right? That gap we will call it is a stride. Okay, local buffer memory. In that memory buffers will be present. Control endpoints somewhat stride can receive or transmit. Therefore, the control endpoints, buffer 0 is always an out buffer. Okay, buffer 0 is always acts like an out buffer, and buffer 1 always in buffer. So because of this, what will happen means simultaneousness will come. Okay, two buffers are there for in and out. Okay, the data from setup and out tokens will therefore always be written to buffer 0. Data sent in response to an in is always taken from the returned from the buffer 1. So a setup phase, what setup phase will do is, setup phase is for uh, it is not writing actually. Before even writing, we will set up the link. That phase is very important. After that, data stage. After data stage, we will get a handshake. See here, setup stage, data stage, status stage. USB IP core data we are writing into buffer 0. We are reading from buffer 0 and data stage. Again, status stage we are writing into buffer 0. Okay. Here, see, USB IP core. This is from the host. This is an output. Okay. Setup. And data packet is also we are sending in setup. Acknowledge obviously we'll get. Okay. So in data stage, this is the in data, which means that data is taken into the uh, uh, taking into the host. So host will give acknowledgement. See, it is simply tells like in PID we'll have some uh, fixed number of bits. It will tells like whether it is a setup or in or out. Okay. So data from the buffer, my host is taking from the IP core from the buffer 1. Okay. So host will initiate ACK or NAC, any handshake signal to the core. Okay. So in status state, USB host, out is So it is telling like out token. See here, you can observe that whether setup or in or out, always it is going from the host to the core. That's what, that's why we will call it is as host centric. So data it is out, which means out of the data it is going. So obviously core should initiate act from the buffer 0. These buffers where it is present, these buffers present in a end device, end point we call it is as. Okay. See these buffer underflow, overflow, these things you people are very much aware. Data organization, how it will look like. See this is 32-bit, this will be byte aligned. Okay. And transfer of the data will always follows the little endian. Okay. You know, little endian, what is meant by little endian means lower byte will go into lower address whenever we transfer is taken. If it lower byte will go into higher address, then it is called big endian. uh, then mixed endian means sometimes it depends upon the requirement. Instruction will give a commands based on that how it will store. Of that no endian means it doesn't follow any endianness. DM operation, you people are very much aware still. DMA operation allows completely transparent data movement between the USB core and the functional attached to the Wishbone bus. This Wishbone bus is open source bus. This is okay. This is open source bus. With the help of this bus only, the data transaction will happen uh, from to transfer a data. You need a bus, right? That Wishbone bus is that open source bus. Anybody can use this without paying license amount. PID sequencing. Okay. Packet identifier. Packet identifier is very key important thing. In that packet will be for a packet first prefix one should be PID. So after PID only we will come to know like whether it is a setup or out or in token. Okay. And also for the handshaking also, whether it is a control in a handshake signal, we don't get any kind of data. We will get only handshake, whether act, knack, NYET or stall. So that also with the help of PID we will come to know. Okay. USB core memory size. The memory is 32-bit wide depending upon the application. The user should choose the appropriate memory size and for the buffer memory. Based on the actual number of endpoints, the memory can be as small as 256 bytes. The maximum supported is 128, 128 KB. These are nothing to do with our actual flash drive memory. This is for any USB core. In the core also small memory will be there. Okay, that is minimum is 256 bytes and maximum is 128 kilobytes. USB core behavior. Okay, here you people need to understand one thing. Okay, full speed behavior, high speed behavior. High speed means 480 Mbps, full speed means 12 Mbps. See, transfer types you need to see it first. Isochronous 1023 bytes packet size. This is 1024 bytes. Interrupt transfer maximum payload size is 64 bytes. This is 1024 bytes. This bulk transfer, mainly bulk transfer is for printers and scanners. 8, 16, 32, 64 bytes, but high speed 512 bytes. one bit at time, how much time it will take. If you calculate from that frequency, you will get 83.33 nanosecond. Here you will get 2 point, here frequency is more, right? So time is less, so 2.0833 nanosecond. UTMI clock, UTMI clock is same for UTMI clock is same for any speeds. Okay, that the clock we call as U clock. Maximum packet delay 7.5 bit times, approximately 62 622 nanosecond, 192 bit times. Why? Because interpacket, if it is high speed, means it is coming very speed. That's why that difference should be very high in a high speed. Otherwise those previous will come and collide with uh, the packet already processing. So to avoid that, we'll keep this time still. 192 bit times is still lesser than 622 nanosecond. This is 400 nanosecond. UTM worst case delay 17 U clocks, 63 bit times, or 8 U clocks, 132 nanosecond. So these the comparisons you people need to go through. PID sequencing. Okay. Isochronous. Isochronous means your mic real time data. Okay. Any real time data will fall under isochronous data PID transfers one transaction. See here, if it is the data, my data is 1023 bytes. Okay, then it will go in a single transfer. At that time, actually, the PID I need to use it for data 0 only. If it is two transactions, okay, two transactions, 532 1024 byte each, then it should toggle the data. First it should be data 0, after that data 1. If it is three transactions, data 2, data 1, data 0. This is for in endpoints. Okay. For out endpoints, one transaction, data 0 only. For two transactions, M data will come here. Okay. And data 1. Three transactions, M data, this is, he forgot it, M data 1 here. M data 1, M data 2. Interrupt data transfers. Always data 0, data 1 toggle continuously and successful transactions. Bulk data 0, data 1 toggle only on successful transactions. Packet errors or mismatches. Packet with address mismatches, ignored or no action taken. Okay. Address mismatch means ignored, no action is taken. Endpoint field mismatch, ignored, no action. The function controller may be interrupted. Packet with bad PID, ignored, no action is taken. The function control may be interrupted. See, whenever a token with bad CRC, ignored, no action is taken care. Uh, this is for control data. Control information we will use CRC file. CRC 16 is for actual payload or data. Okay. Ignored, no action is taken care. Unsupported token. Okay. Ignored, no action is taken. Tokens. Pre-split token. Pre-token split. We will split the token also. Sometimes whenever we want. Okay. SYF start of frame. Frame number is recorded in the frame NAT address translation. Okay, register. The number is same as previous. The same field is frame NAT register increment. The whenever this SYF come, frame NAT register will increment by 1. The counter will be present here. Ping token received and have the space for maximum payload size. Not applicable. Ignore, no action taken. Issue acknowledgement handshake. See here, ping token received under no space for maximum payload size. Issue NAC for high speed. For full speed, we don't care this. Ping token received and halt mode is there. We don't care in full speed. Output, see here, halt mode is set here already. So we need to issue stall handshake. In endpoints, similarly out endpoints, you need to go through. USB core flow charts. Okay, main loop. See, this is initially ideal. USB core received token. Any token, if token is received, token corrupt. Yes, report token is corrupted. Error, decode what kind of it is. Ping and SOF are special. Here, setup in token, out token, perform setup cycle. All those cycles we need to perform. That's all. Okay, again, for each processing also we'll have this state missions. Okay, this SOF or ping. Special one means halt mode. All these things you people need to go through. These are simple one only. USB, see here, USB device control processing. Power on, function reset. Okay, power on, reset. Actually, function reset, power on, reset, both are same only. At one time only, at one passage of the clock it will turn on. uh, Switch to the first initially FS mode. Wait for 100 millisecond. Okay, J asserted, this is chirp J. Okay, we'll call chirp sequences. Bird will chirp, right, uh, to get acknowledged for the its female version. Here also it will chirp. Okay, set attached to flag. So its according flag will be attached and chirp. Normal operation. See, idle for greater than 3 millisecond and full speed mode suspended. If it is ideal for asserted for greater than 3 millisecond HS mode, high speed mode, switch mode to the FS. If it is there, then from high speed to the low speed. In low speed, low power will be consumed. High speed, high power. So we will consume less power in HS. Sorry, FS. So after switching to FS, we will after 3 millisecond again 100 microsecond we will wait. If it is still ideal, then we will J asserted, chirp J asserted, we will go to the suspend. Okay. If it is if any see if it is for example zero comes, single ended zero assert, we will go to the reset. See, after normal operation, ideal asserted for greater than 2.5 microsecond but less than 3 millisecond. We will switch into FS mode. See, from ideal, okay, J for full speed, yes, single ended 0 for HS speed, okay, high speed. From the suspended to resume, okay, normal operation. How it will happen? Suspended, set suspended mode, okay, that mode got suspended. SE0 asserted for 2.5 microsecond. Okay, it will go to reset. Okay, here chirp K will be there. Chirp K will be clear suspend mode and what we will do, single-ended zero asserted on HS mode. Switch it to HS mode. After that normal operation. Or else it will go to single-ended asserted mode and full speed mode will be there directly. Here switching operation takes place here directly FS mode. Here clear suspended, here first we will clear suspended mode, wait up to 10 millisecond, drive K for 1 to 15 millisecond. Okay, after that single ended zero asserted and we'll go to the HS mode. See, again on fly reset, fly on reset, FOR we call it as. Okay, when reset appears, then signal reset internally. If my transaction data is transferring, for example, okay, continuous data in the middle of the data, some reset word asserted, then how it will behave? Then send chirp K for 1 millisecond. Okay, wait for chirp K. Chirp count 6. So 3 pairs actually. Got single ended 0. Got chirp J sequence. Chirp count equal to 6, which means 3 pairs. Chirp got chirp, wait for chirp J. So these will get pair. After that, whether to operate in a normal mode, normal operation, switch to HS. Normal operation means if it is in FS mode normally, or else if you want to switch to highest mode, the high speed mode we will do. Here, int A, int B, two types of interrupts will be there. Suspended resume. I explained that operation. Please go through. Core registers. See here, CSR. CSR 32-bit register, control and status register. Functional address register will be present here. This is offset addresses. This is its width. This is its access. Read write means we can either read or write. We will configure actually. See, ROC means uh, read only after that clear. Read once after that clear. Read only. See, interrupt means first we will read only, after that we will clear. Once that operation was initiated, then we will clear. Read once clear. Read only. Read write. Read once clear. Write only. Like that different registers will be there. Interrupt source. Format NAT we discussed already. Frame number and time. Okay. UTMA vendor. This is vendor specific IO port actually. Endpoint. These are the endpoint registers. Endpoint 0 CSR, interrupt, buffer 0, buffer 1, CSR. These are for these three for endpoint 0. Sorry, 4 for endpoint 0. Again, same 4 for endpoint 1. After that, endpoint 2. Okay, in endpoint 2 we will get in. Okay, endpoint 3 in, endpoint 4 in. So after that we will get only out we will get only for special registers. Okay, function address. See, each register that bits, everything was explained here. You need to go through. Okay, this is this offset address is 00H. Okay, value after reset.